Oh yeah, it looks the same to us.
All right, good. Thank you for letting me not worry about that. All right, let's go. I just started recording, so let's go ahead and start. We had, right before class, we had some discussion about the exam you just took, and I'll hang around after class and answer questions about that. And we can always discuss stuff online, especially, and we've got a regrade policy if anything happens that looks like it's unfair. The thing I'm talking about is I had to go in and fix a couple of questions early during the exam. So if you took it kind of right at the start of the window, you might have been affected by that. I'm going through the material we covered last time. We talked about the tail end of the standard library stuff. And then we talked about some tricks for designing a component. And we were looking at different ways of organizing our code to try and achieve a couple of things. One of them was to hide as much of the implementation as we could. And we came up with this idea, or at least we learned how to use this thing called name-only use. And we already did this last time, but if you tell the compiler about a struct, it'll let you use pointers to that struct, even if it doesn't know anything else about what's in the struct. And that is enough to let client code use a type where the definition of that type is hidden. And hidden is good because it's details that are hidden are usually details that you can change later. And the last thing that we wanted to do with this, and this is kind of this is where we stopped last time. This was a week ago today. We said, could we make this thing generic? Could we make it so that instead of just being a set of integers, it could be a set of anything you want? Not mixed types, but if you wanted a set of integers or a set of doubles or a set of strings or anything like that, we ought to be able to support that. And we would call that a generic abstract data type. And like some people volunteered, you've been doing that in your data structures class a lot. The generics mechanism provided by Java gives you a good way of doing this. In C, we're going to have to do more of this ourselves, but we can still do it. What we're going to do is we're going to keep the representation of the data structure. So we'll have a generic linked list that could hold a linked list of anything. We'll just be able to reuse it for any type of thing you want. One thing that's going to have to change is what I'm trying to show here. Since the size of the thing in our set could vary, like if you wanted a set of integers, that's 4 bytes for each value. If we wanted a set of doubles, that's 8 bytes for each value. If you wanted strings, they could be different sizes per value. If that's what we're going to have to deal with, it means we're not going to be able to store the value inside the nodes. We're going to have to store it separately. So we're going to go from a representation that looks like this top picture where each node contained the value it was storing, down to this bottom picture where every node kind of contains a pointer to the value it's storing. And we'll use a generic pointer for that, a void pointer in C++ or in C. Notice this is what Java does already. Java's generics mechanism lets you keep up with any type you want, but it has to be a reference type, because even in Java, they're doing the same trick that we're doing here. Objects that have a type parameter, that type parameter always ends up being replaced with a reference type, not a value type. So essentially a pointer in Java. One trick we're going to have to do with this is, well, if you think about it, to implement a set of any type of item we want, we still need to be able to compare items. Like if you try to put an item in a set, we need to be able to look through what's already in the set and say, is this already there? The problem is the way to compare items depends on the type of item we're storing. And that's going to be chosen by client code. We're going to try to make a set that can hold any kind of thing you want. But how to compare that thing, like if you have to compare strings, there's one way to do that, and that depends on strings. If you need to compare doubles, you need a different comparison operation. So if this is how our code is going to look, the set is going to implement the data structure, but whenever it needs to compare items, it's going to have to ask the client code to do that. So we could treat these as two different components that use each other. The client could make calls to set whenever it needed to make a set or put an item in a set. And then when set needed to compare something, it could just call functions in client. That's what I've drawn here. And I drew it to make the point that this is a terrible idea. This is what we might call circular or cyclic dependency in our code. And that's something to avoid in C or in Java or just about any programming language. You don't want to organize your code so that you've got component A that depends on component B, and component B also depends on component A. Code like that is harder to understand. It's harder to implement. It's definitely harder to test. So we'd like to pick a direction. Client can use set or the other way around, but not both. So we're going to fix this by going with the dependency we had before. This is one reason why in a lot of our projects, we show a picture that shows at least our plan for how the code is going to depend, or how the components in the code are going to depend on each other to kind of help us think about this kind of thing. We are going to let client use set. It's going to supply not only information about what gets stored in a set, but it's also going to tell set how to do the comparisons. So if it wants to store a set of strings, it's going to have to say, well, here's how big a string is, here's how to make a string, and whenever you need to compare strings, here's how to do it. It'll do that by providing a function pointer to the set. So essentially, some people would call this a callback, a way of telling the set whenever you need to compare things, here's how to do it. Here's a function that can do it for you. This is the same trick that qsort used. It can sort any items we want, but to help it do its job, we have to provide a pointer to a comparison function. And as long as it knows how big the array is it's sorting and how big each item is and how to compare items, that's enough to let qsort do its job. We're going to write code that works kind of like that. It's just our set will need to know more than just a linked list of a fixed type of item. Here's what it seems like it's going to take. So here's our last implementation of this component, now made into a generic set. We're doing the same tricks we did before. We're trying to hide our implementation. So we've got a header that just gives away some type names and some prototypes for functions. But we've snuck in our design, in our data structure, now set does more than just keep up with a head pointer. Here's the head pointer, same as before. It's a linked list of these nodes, but notice the nodes all have a next pointer, but for the value, we made that a generic pointer, a void pointer. So it could point to anything we want. Backing up a couple of slides, that's what's going to let us do this. Every node has a pointer to the value stored at that node. It's just, we depend on it being stored somewhere else in memory. So here's each one of our nodes. In the set, in addition to our head pointer, we're going to remember two things. One is, how big is each value? I tried to make the point that, well, for a set of ints, every value is 4 bytes. For a set of doubles, every value would be 8 bytes. For a set of strings, you could have a maximum length for each string in the set. So every set's going to remember that, and it's going to remember a pointer to a function. You know, the syntax here looks a little ugly, but you're probably getting good at reading this by now. So same as a function, it's pointer to a function where you give it 2 items in the form of void pointers, and it returns true or false, telling you if they're the same or not. When you make a set, you have to tell us these 2 things. Notice the make set function got a little bit trickier. It gives you back a pointer to a set, but you have to tell it how big each item is in the set. That's what this v size is. I think of that as the size of a value. It's just a number of bytes in memory for each value. And you have to tell me a pointer to the comparison function. And then I'll malloc space for the set. I'll make it an empty set initially. I'll fill in copies of the two things you just told me. So you won't have to tell me these two things over and over again. You tell me when you make the set, and then whenever you use that set, it knows how big each item is, it knows how to compare them. The functions, this is one of our 4 functions. The other 3 are posted with the example today. They use the stuff in the set struct to allocate space for a new item, or at least a copy of a new item whenever you put it in the set, and to call this comparison function whenever you ask if an item is in a set. So if you want to take a look at those, they're same idea as this, just 3 additional functions. What does the client code look like? Well, now if you want to make a set and it needs to be generic, you have to supply these 2 extra things. How big is each item, and how do you compare items? Let's say you still want to just make a set of an int set of ints using this generic container. Well, you're going to call make set to say, make me a set. Each item in the set is however big an int is. So we just get size of to tell us that, and we pass that on to make set. And we wrote our own comparison function for comparing ints. Here it is up here. Whenever set needs to compare items, it'll call this function, and you can see this function. It's kind of like the comparison function you might use in Quicksort, just a little bit simpler because it just has to say yes or no. It doesn't have to worry about ordering items. So here it takes the 2 void pointers it gets, but since we're writing this set ourselves, we know that they secretly point to 2 ints. So we take those 2 pointers, we cast them to int pointers, and then we dereference them to get the ints they point to, and then we return true or false based on whether those integer values are the same. So this makes a set. This inserts values into the set. We didn't see the code for this, but to make this work as a generic data structure, instead of passing a copy of the value you want to put on the set, we have to pass a pointer to it. So this is kind of a sneaky trick to get a pointer to an int 2, a pointer to a 3, a pointer to a 5. I'm doing it by making an array that just contains 1 value, like this 5 here. But since it's an array, this evaluates to a pointer to its first item. So this line gives me a pointer to a 5 without having to make a variable that holds it and then take the address of that variable. This lets me do it all in 1 line. So I put 5 different items on the set, and then I go through and ask, does the set contain each of the values from 0 up to 12? And then when I'm done, I free the memory for the set. We didn't look at the code for this, but same as before, it walks down the linked list of items, freeing each node. That gets us caught up with where we should have been at the end of lecture a week ago. Questions before we switch to today's material? All right.
So I saw,
Go ahead.
I saw this question in the chat, but I'll just ask it.
Sure.
For like the 2, 3, 5, 7, 11, why don't you have to malloc them since you're passing them into a different method?
So we didn't see the code for this, but it's posted. Back here, when I looked at the implementation for set, we saw make set, but we didn't see the implementation of insert value. But to make this generic, we had to pass a pointer to the value, but inside the set, it makes a copy of that value. So here, again, we didn't show the function for this, but it's right after this.
Is the file the set1.c?
I think it's set4.c. So 1 was the first one we did, and then we made it a little smarter and then a little bit smarter. I've got it here. Well, maybe I don't remember if I counted from 0 or if I counted from.
I think you counted from 1 because it starts at set0.c.
Yeah, I apologize, and I copied the lecture 20 examples over instead of instead of
Yeah,
19.
set 3.c.
Yeah, so I started with 0. So the one we're looking at here is set 3.c. So this is the generic one. And you can see, this is the way I always try and do it. I put a lot more comments in the examples than I can fit on the slides. So here's a description of what we're doing. Here's the make set we just looked at. And then here's what we were just talking about. So you give me the set you want to put an item in and a pointer to the value you want to put in. And then we check to see if it's already in the set, in which case we're just going to ignore it. And then this is kind of the answer to your question. If it's not already there, I'm going to make a copy of it anyway to store in the set. And then I'll just free it when we remove that item from the set. So here's where I'm copying enough, or I'm malloking enough memory to hold a copy. And then I copy whatever value you gave me. Your actual question was, client 3. So this is the client code for that. And down here, the reason I don't malloc these is I could malloc them, but then they're just going to get copied again later, and I'm just going to have to free them. This stack allocates space for a 2, and it gives me the address of it. So it's kind of like you made a variable that held a 2, and you passed its address. I just don't have to bother declaring a variable and then using it on the next line. I can do it all in one line. It's kind of, well, I mean, it's clever, it's ugly, but it works.
Okay.
All right, other questions? All right, so that's sort of a continuation of what we did on lecture 6 when we first started learning how to write a multi-file program. And here at the end of lecture 19, we kind of revisited that and said, well, what are some choices for how we could design and implement a component? The real material we're supposed to cover today is part 2 of data structures, and we'll talk a little bit about object orientation in C. And like I'll say a couple of times later, when we learn how to do object orientation in C, we'll really be learning how it works in a language like Java, because we're going to have to do some of this stuff ourselves. First, I want to revisit the pointer-to-pointer syntax that I first mentioned when we started doing linked list. I tried to sell you on this idea that if you're willing to keep pointers to links in your linked data structure, whether that's a linked list or some other linked data structure, it can really simplify your code. You have to get used to writing code that works with the address of a pointer, but it can simplify some things. So I wanted to revisit that just so we can talk about the syntax in a little more detail. And then we're going to apply it to not just a linked list, but a binary tree, where it'll save us even more code. So I want to sell you on this idea. And I'll do it by backing up a little bit and saying, well, a pointer is handy. A pointer to a node can let you keep up with what's in that node. So if this is a linked list, and you had a pointer node that was pointing at this node with the 9 in it, that pointer is handy because it lets you get at, just like I said, the fields of the node it's pointing to. And that's what I'm showing here. If node is pointing at this struct with the 9 in it, then node, and I probably skipped over this slide where I said same representation we used a couple of lectures ago. Every node has a value and an X pointer, and there's a list structure that just has a head pointer in it. So that's kind of what I'm using here. So I was trying to make the point that if you had a pointer to a node, well, node arrow value will give you its value field, and node arrow next would give you what its next pointer is. So a pointer is useful, a pointer to a node is useful for getting to the stuff in that node. A pointer to a node is at least as useful. And that's the point I want to make here. How about if instead of keeping up with this 9 node by keeping up with a pointer straight to it, how about if you keep up with a pointer to the pointer that goes to that node? Well, this is still pretty useful, because if you've got a pointer to this pointer to the 9 node, then you could just stick a dereference on it, and then you've got a pointer to the node. So a star, so if link is the name for your pointer to the pointer to this node, then starlink is the same thing as a pointer to the node, including you can get to the fields in that node. So a pointer that went straight to this node lets you get to the value field, but you can still do that. If you dereference this pointer, if link is a pointer to this pointer to a node, well, if you dereference link and then use arrow value, it'll give you its value field. If you dereference link and then say arrow next, it'll give you the next field. So you can still get to the fields in that node, even if you've backed up by a pointer and you have a pointer to the pointer to this node. But you can also do other things, like if you assign to link. So link is a pointer to a node. You can make it point to any pointer to a node you want. This silly picture here, I'm sort of showing you can make it point anywhere you want. So if you just assign to link, you're deciding what pointer it points to. If you dereference link and assign to that, you're changing the pointer that points to that node. So link equals something will change where link points. Star link equals something will change where this pointer points. And that's what we talked about before. That would let you change the structure of the list. If you knew the address of some pointers in the list, you could use that to change those pointers and to move nodes around in your list. We can write some awfully simple linked list code by keeping up with, or at least by writing code that's not pointing directly at a node, but is pointing to the pointer that gets us there. If we wanted to do that, then traversing the list would involve taking a pointer. You could think of this pointer, if you think of it as keeping up with the node with the 9 in it here, it's a pointer to the pointer to that node. If you wanted to traverse the list, you just need to be able to move ahead by an item. So like my picture shows, you want to be able to take link, and instead of having it point at this next pointer, you'd want it to point at the next pointer inside the next node. Well, that's easy because we already know how to get that next pointer. We just said that a couple of slides ago. So if you take link and you dereference it, star link, well, that's the pointer to this 9 node. If you put an arrow next on that, that's the next pointer inside this node. If you take the address of that, and that's this ampersand in front, then that's the address of the next pointer inside this node. And if you just make link point there instead, that's what I'm doing right here. Now link is pointing to the next pointer inside the next node, inside the node with this 9 on it. If you did this again, then it would be holding the address of the next pointer inside this node with the 42. So this gives us a handy way of traversing a list by moving through its pointers, by moving through the addresses of its pointers. We could also use this to change the structure of a list. And this is what we did before. I'm just talking through the syntax a little more gradually. If, let's say we wanted to remove this node with the 9 in it. If we take link and we dereference it, and then assign to that, well, if you take link and dereference it, you're talking about this pointer. If you assign it to that pointer, you can actually change where it points. You could make this next pointer point somewhere else, including skipping over this node. And that's what we're doing down here at the bottom of the slide. If you take link, dereference it, that's what we're doing in the red part over here on the left, and you make it point somewhere else, specifically, you go get a copy of the next pointer out of this node with the 9 in it. Well, that would be a pointer to this node with the 42 in it, and you assign that to the pointer that link points to. You dereference link, and then you say, now I want that pointer to point to whatever came after the node with the 9 in. And that's what I'm doing down here. Then you've just removed this node from the linked list. The nice thing is you can do that for any node in the list, including the first node. That would work just fine if link was pointing not at the next pointer inside a node, but the head pointer for a list. It would give you a way of writing the same code to remove a node, whether it's the first node in the list or some node later in the list. We already did that. We did it when we first learned about linked lists, but this same trick can simplify a lot of code for linked structures. So instead of doing this with lists, I thought we'd try it with a binary tree. You know what a binary tree is. It's made up of a collection of nodes, kind of like a linked list, except instead of being ordered arbitrarily, they're ordered left to right. So every node could have a left child and it could have a right child. And every node, the key in its left child is normally less than the key value, the value at that node. And the key in its right child is normally greater than or equal to the key at that node. This is a data structure. It's a lot like the linked list one we had. But we could use this to build trees. So now every node has a value in it. When I was talking about the keys and the left to right ordering, that's really what I was talking about. And a pointer to its left and right child nodes, or null if it doesn't have a left child or a right child. I made a short name for node using typedef, so now I can just call it node without even having to say struct. And then I've got a type for the whole tree. So kind of like we had with a list, this tree struct just has a root pointer in it, but you can think of it as representing a whole tree of nodes. So we could use this to build a binary search tree like this. It follows the ordering we just talked about. You could pick a node like this 50. And sure enough, its left child has a key that's smaller and its right child has a key that's larger. Whenever we want to, and of course, you know from your data structures class, this can be a very efficient way of organizing sorted values, especially if we do some extra tricks to try to make sure our trees stay short and fat rather than getting tall and skinny. Normally, inserting a value in a tree is a little bit tricky just because of the different cases you have to worry about. If you have a node and it goes to the left, you have to change the left pointer. If you have a node and it goes to the right, you have to change the right pointer. But the trick we were just talking about could make this easier, because even though these two pointers are different fields of a node, they have the same type. So if I manipulated the tree by keeping up with a pointer to the pointer to the subtree I'm looking at, we could avoid a lot of special cases in this code. And that's what we're going to do here. We're going to look at some code for inserting a node into a tree. But instead of just looking for the node where we need to add that as a child, we're going to keep up with the pointer we have to change to insert that node. And we'll call it the same thing we did in the previous example. Link, we'll say, is a pointer to the pointer that we might have to change to insert a child. We'll start it out pointing at the root pointer. So initially, we're going to look for the place where we need to insert this child. And until we've learned otherwise, maybe we need to change the root pointer to put in a new child. So link will start out holding the address of the root pointer, but it's going to descend the tree looking for the pointer that we need to change. So let's say we're inserting a value like 30. Well, link starts out pointing at the root. The root is non-null, so there is, at least in this picture, if the root is non-null, then there is a root node of the tree. So we can compare 30 with that, and that'll tell us if we need to go left or right. 30 is bigger than 21. So until we see otherwise, the pointer we need to change is this one right here, the right pointer out of that root node. So as we traverse this tree, that's what we're going to do. Link needs to move down the tree, and instead of being the address of the root pointer, once we see that 30 is bigger than 21, it needs to be the address of the right pointer out of that 21 node. And then we'll just descend the tree like that. There is a right subtree of this 21 node. Sorry. And it's got a 50 on it, so 30 goes to the left of that. So the next place we need to go is link will be a pointer to the left pointer in this node with the 50 on it. That pointer is non-null. The 30 is less than the 42 that it points to. So now link will be a pointer to the left child of 42. If 30 goes in the tree, it's going to involve changing what's in the left subtree of 42. And now we're just about done because we found a null pointer. We kind of hit a leaf of the tree. 42 has no left child. It's a null pointer. And we've got the address of the pointer we need to change to graft on a new node. So all we have to do is malloc space for a new node that has a 30 in it. We have to change this one pointer, and that would have taken the same code whether it was a pointer to the root pointer, a pointer to the left pointer out of a node, or a pointer to the right pointer out of a node. Those are all pointers to nodes. And if we know which pointer we have to change, it just takes one line of code to graft in this new node. Here's the code it takes. So this is what we just talked through. It's not a balanced binary tree. That would be trickier, but it maintains the sorted order, and it handles inserting into a tree, folding together a few different cases by keeping up with what we've just been talking about, the address of the pointer we have to change. Same as the picture we just looked at, link is going to help us find the pointer we have to change. It does it by keeping the address of a pointer within the tree, and it starts out holding the address of the root pointer, just like we did in that figure. And then we're going to go look for a pointer that's null. So maybe the root pointer is null, maybe we're going to descend the tree and find a null pointer, but as long as link is pointing to a non-null pointer, as long as the pointer we're looking at is non-null, we need to keep moving down the tree. And that's what this while loop says. We dereference link, so that gives us the value of the pointer it points to, of the thing it points to. And as long as that evaluates to true, it's non-null, so we keep moving down the tree. If link points to a non-null pointer, then we can look at its value. And that's what we do next. This is a special case. Maybe the value you're trying to insert is already in the tree. And if we find it, we just bail out with a false. We don't even insert. Otherwise, we decide if we go left or right. If the value you're trying to insert comes before the value on the node you're looking at, then we move left. Otherwise, we move right. This move left and right is almost the same as what we talked about with the linked list code. We dereference link. That gives us a pointer to a node. If we have to move left, we get the left field in that node, and we take its address. That's where link needs to point now. If you need to insert this item until we see otherwise, you're going to insert it by changing the left pointer out of the node you were just looking at. Or if value is bigger than or equal to the key at that node, you go right. Same code, we're just getting the address of the right pointer out of that node. So this while loop moves down the tree until either we find the node we were about to insert, in which case we bail out, or we find a null pointer. If we find a null pointer, we don't just have a copy of a null pointer. That wouldn't be useful. We have its address, which means we can change it. And that's what makes the rest of this code really easy. We found the pointer we have to modify, and since we have its address, we can modify it. We malloc space for a new node, we fill in its val field. It's going to be a new leaf node, so I set its left and right pointers to null. You can do this in C. You can also do it in Java. Assignment associates right to left. So you can read this as, and you probably saw this in Java, assign null to the right pointer in that new node. And then this still evaluates to null, so assign that to the left pointer in that node. So this lets us initialize both of them with one line of code. And then this line right here is where we actually link it into the tree. We take the pointer that link has the address of, the one we need to change, and we make it point to this new node. And then we're done. And I would say if we had to do a balanced binary tree, this would definitely get trickier. But this is some awfully short, simple code for inserting into a binary search tree. And one thing that makes it simple is we can fold together a lot of different cases by keeping up with the address of pointers rather than just the address of nodes. That's all I got to say about pointer to pointer for now. Questions before we try to move on? All right, like I promised, we're going to do some object orientation in C. C wasn't made to be an object-oriented language, but even when people were doing a lot of programming in C, they appreciated the value of object orientation. And there's been a lot of object-oriented code written in C, just with the programmers having to do a lot of work of writing it. That's one reason C++ exists. It exists to have a language that's basically C with some additional object-oriented features and some other stuff we'll talk about later in the semester. If we want to write object-oriented code in C, we're going to have to do a lot of the things that a compiler would normally do for us. We're going to have to implement a lot of the object orientation ourselves. But in doing that, we're going to see how object orientation really works, even in a language like Java. So the tricks we're about to see, they're simplified. We could do some of this stuff more cleverly. We could save some memory. But they're basically the same ideas Java or other object-oriented languages use to provide efficient object orientation. We're going to introduce features one at a time, kind of like we did with the set example we were working with before. So I'll describe a motivating example, and then we'll start with a simple version of it, and then we'll add more and more features. And as we do that, we'll be implementing more and more object-oriented tricks. So our motivating example is going to be something like a spreadsheet. It's going to be a grid of cells like this picture shows. In fact, the spreadsheet we're going to implement can draw a picture of itself like this by just printing out characters and showing what's in each cell. It'll be implemented as a two-dimensional array of cells, but the cells themselves will try to fake objects for those. So we'll implement in C something that works a lot like an object in C++ or even a Java object. And that's going to include inheritance. So we're going to implement what looks like a superclass called cell, and then we're going to implement subclasses that store different kinds of values. And by the time we're done, we'll have a subclass that stores what looks like an amount of money with dollars and cents. And we'll have another subclass that can store strings, arbitrary, text. We'll even have a base class that implements kind of boring behavior. It doesn't print out anything. It kind of represents an empty cell. Oh, I caught myself saying base class just now. And that's because C++ uses base class and derived class to mean the same thing that Java means when we say superclass and subclass. Until we switch to C++ at the very end of the semester, I try to use the Java language because I know that's what you're accustomed to. So I should have said superclass, but I occasionally slip up and use the C++ terminology. So we're going to make a superclass that represents an arbitrary cell, and we're going to implement our own subclasses for this. And we want these to exhibit inheritance. We want to be able to build a spreadsheet where the cells can be filled with different types of objects. So how are we going to do this? Well, we're going to define two different structs. One for the superclass. We're going to call it cell. And the only thing the superclass is going to have is it'll know how wide it needs to be. So it'll know the horizontal number of spaces that it wants to have to lay out nice, for the organization to work nicely. We're also going to make a subclass that's for storing money, and we'll call it money. It'll store, I think it's going to be a floating point value. I don't remember how I did this. But it is posted with the examples for today. So it'll maintain an amount of money, and we'll make it so that money objects work just like cell objects. So you can use an instance of the subclass as if it was an instance of the base class, of the superclass. And this picture shows how we're going to do that. We're going to design these two structs so that anything they have in common is at the start of the struct in memory. If you looked at a cell, if you looked at the superclass, well, we already said it has a width field. So that's the only field it's going to have for now. Well, money needs to look just like a cell, maybe with some other stuff. So we'll make another struct for that, but we'll start it out with fields that look exactly like cell. So in memory, money is going to start out with a width field, exactly the same size in memory, exactly the same place in the struct, but then anything that needs to be added by the subclass, like the value for a money cell, the amount of money that it stores there, we'll add that afterward. The reason for this trick is, well, if you just had a pointer to a cell, you wouldn't really care if it was the superclass or some subclass. Probably a better way to say that is if you had a pointer and you were only going to use it as the superclass, it would work fine for cell or for money. If you had a pointer and you were planning to use it like cell, like the superclass, you would expect to be able to dereference that pointer and find a width field right there in memory. Well, if we are careful and we lay out money so it's organized the same way in memory, then if you had a pointer to a money instance and you dereferenced it, you'd find exactly what you'd expect. You'd find a width field right there at the start of the money object in memory. Maybe there's some other stuff after it. But if you were only counting on having the stuff that the superclass had, only the width field, then you'd never go look at that stuff anyway. So this is how we're going to make subclasses that inherit from their superclass, that look like they are, like they have all the stuff their superclass has. We'll just make sure that anything that's there in the superclass is also there in the subclass in exactly the same relative location in memory. So we just need to build a couple of structs that are organized like this. And here's what it would take. So for the superclass, we'll have a type def for a struct called cell, and all it has is a width field. For the money subclass, it's a different struct. We're going to use it as if it's a subclass of cell. So we put the same width field right there at the start. But if it also has other fields that only a money object should have, we'll add those afterward. And I can see here I guessed wrong a couple of slides ago. I couldn't remember if I had made that floating point or an integer. It looks like I made it an integer, so it's probably counting the number of cents in that money amount. So by organizing them like this, the point is if you had a pointer to sell, or if it was really a pointer to this subclass money, it should look the same to you in memory. It starts with an int. What else would we want for an object? We'd probably want something that worked like a constructor. And we already know how to do this in C, or this kind of thing. We've done this on, I think we're doing it on the current project, and we probably did some stuff like this in project 4. We could just make a function that does the job of a constructor. We'll need one for each of our types. So when you call make cell, you give it the width. It remembers that in the cell object, it dynamically allocates space for an instance of cell, fills in the width field, and then returns a pointer to that. So this makes a instance of the superclass and gives you back a pointer to it. Down here, we do the same thing for the subclass. If you ask to make a money object, you have to give me both the field that the superclass needs and this extra field that the subclass needs. We'll allocate enough memory to store both of those. We'll fill in both of those fields and then return a pointer to the money object. So this is what constructors for these two things look like. Notice we are returning the objects not by value, but by reference, by pointers. In fact, let me back up and say, for this trick to work, when I say this trick, I mean being able to use a money object as if it was really a cell object, because we made it start out looking just like a cell object. It's got the same types of fields in the same order. We just had to do it ourselves. For this to work, we have to get to objects by pointers to them, not by passing copies of their values around. So for this inheritance trick to work, we're going to have to use pointers to these structs rather than passing them around by value. And so we did the same thing here in their constructors. When you make one of these cells, you get back a pointer to a dynamically allocated instance of either the superclass or the subclass. Notice this is how Java works automatically. You don't get a choice in Java. Objects are always reference types in Java, which means they kind of work like pointers. And when you access their fields or when you call methods on them, you're always accessing them by references, essentially by Java's version of a pointer. In C, we could pass structs around by value rather than by address, but to make them work like Java objects, we're going to have to use the same tricks Java does. We're going to have to keep up with those objects by address rather than using value semantics for them. So here's how we could make objects with essentially our own fake version of constructors. Here's how client code could use them. Let's say we're going to make a spreadsheet that's got 2 rows and 3 columns. So that's an array, a 2x3 array. Every cell needs to be able to hold, every element of this array needs to be able to hold a pointer to a cell. So that's what I made it, or that's how I made it. Sheet is a 2x3 array of pointers to cells, kind of like I'm showing in the picture. When I make the array like this, all of those pointers are uninitialized in C, so I better make them all point to objects if I want to use them. So that's what I do. I go through, I just hard coded this for every element of the array. I make it point to either an instance of the superclass or an instance of the subclass. So when I call make money, I'm really getting an object that has these 2 fields in it. When I call make cell, I'm really getting an object that just has this 1 field. But as long as you're going to use that pointer as if it was a pointer to a cell, you're going to find exactly what you expect when you dereference the pointer. Whether you follow a pointer to the superclass or a pointer to one of its subclasses, you'll find the width field right there at the start of the memory that pointer points to. Questions?
Why did you cast for? and
Right
not
here?
Excel.
Yeah,
Yeah.
that was next. So it is unfortunate that I have to do that, because if I was in a real object-oriented language, it would know that cell is a superclass and money is just an extension of it. But C doesn't know that. It doesn't know what I'm trying to do. If you back up a couple of slides, well, I made a struct here that's got a width field, and I made a, as far as C knows, this is a completely different struct. I was careful to make it start out looking just like cell, but C doesn't care about that. It says, oh, this is a completely different struct. I just designed it with the plan that I can use one of these as if it was one of these, as long as you don't look past the width field. Well, since C, so this is the disadvantage of do-it-yourself object orientation. Make money returns a pointer to a money object. If you back up, yeah, it says when you make a cell, you get a pointer to a cell. When you make money, you get a pointer to the derived class, but the compiler doesn't know anything about derived classes. So when I get that pointer, if I want to use it as if it's a pointer to the superclass, I have to do the cast myself, because the compiler, as far as it's concerned, these two structs don't really have anything to do with each other. I just made it so that they organize them so that you can use the subclass as if it was an instance of the superclass. That was a long-winded answer, so I hope it was an answer to your question. Any other questions, or if you want to re-ask that question? All right. So this makes a spreadsheet and fills it with cells. Once you've done that, what could you do with the spreadsheet? Well, our first version of this really just prints out the borders around the cells. In fact, I deleted a bunch of this code to fit it on the slide, but I kept the important stuff. If you want to print out the spreadsheet, well, here we iterate over all of the cells. Here, just for convenience, I go get one of the cells, it's a pointer to a cell, and I copy it to a cell pointer variable. That's just to shorten the syntax a little bit. So I've got a short name C for the current cell, and they all have a width field. So if I take C and use arrow width on it, whether it's a pointer to a real instance of the superclass or this money object that I was careful to make sure starts out just like the superclass, you're going to get what you expected. You're going to get the value of the width field. And this syntax, I don't think we've really seen this, but this percent star S says print out a string, but let me use an argument to specify the width. So you can plug in a variable for the field width. So this is just a lazy way of printing out each of these cells with a width that's determined by the cell. So this prints out a bunch of boxes, but it doesn't print what's in the cells. We're going to add that. We'll need to figure out some more tricks for doing that, but this at least uses superclasses and subclasses interchangeably, really the same way Java does it. The Java language supports inheritance, so you don't have to do that as much of this yourself. But when you make a subclass in Java and you say what it inherits from, the compiler automatically builds a new representation for that that starts out looking just like the superclass. And any new stuff that gets added, it puts later in memory, so that if it knows where an instance of that subclass starts, at the start of that memory, it looks just like an instance of the superclass. What else would it be nice to do? I guess if we allocated space for all of these objects, when we're done, we need to free all of that space. Right now, whenever we allocate an object, if you look inside the constructor, back a couple of slides, it just calls malloc and fills in the fields. So when we're done with an object, we could just call free to give that memory back to the heap. So that's what we do in the client code, at least in our first version. We go through every one of the cells. We call free on the pointer to that object. And since each object is contiguous in memory, an instance of the superclass is all in one big block, an instance of the subclass is all in one slightly bigger block. Since those were each malloc with malloc, a call to free will free either an instance of the superclass or an instance of the subclass. What should we add next? Well, one thing that's kind of bad about our implementation, if you back up a slide, here we're letting client code access one of our fields directly. And for object-oriented programming, we probably wouldn't do it that way. We would say, oh, if you want something that this object knows, you've got to call one of its methods. I'm not going to let you directly access a field. So instead of just looking inside the object, it would be nice to have what worked kind of like a method on the object. And even if that method just looked at the width field, at least we'd have a functional entry point for getting to the width rather than just having client code directly access the representation. So that's what we're going to do next. We're going to write a fake method for the superclass. I say it's a fake method because in C, all of our functions are, there's plain old functions. They're not part of an object. They're what people would call free functions in an object-oriented language. They're not hidden inside a class. So if we want a method like getWidth that works for a cell, it's just going to have to be a plain old function, not part of an object. But you're going to have to pass it a pointer to the object it's supposed to get the width of. So we'll pass that in as the first parameter. This is kind of like an instance method. We just have to help it out. You call getWidth, and you give us the object that we're supposed to get the width of. This is secretly how instance methods work in Java. You don't really have to pass in the object they're supposed to work on. Usually if you were calling getWidth, it would be something like object.getWidth. But if you look at what's happening inside the virtual machine, and if you look at the Java bytecode, it's doing the same kind of thing. When you call an instance method, it's passing the reference to that object as the first parameter to that method, kind of as a secret first parameter that you don't really have to pass, but it happens internally, automatically. Here, we just have to do it ourselves. So to call getWidth and have it get the width of a particular cell, we have to tell it the cell. And then given that pointer to a cell, it can go use the arrow operator to get its width field and return that as an int. The nice thing is, this is already inherited by the derived classes because we took care of that when we were designing the struct. And I've got a little picture over here to try to remind you of this. We designed the superclass and the subclass so they both have a width field right at the start of their memory. So this code, if it says, well, give me the pointer to a cell and then go get its width field, if that pointer is really pointing to a cell object or one of its subclasses, then it's going to see exactly what it expects right at the memory that pointer points to. So this function will work just fine for either the superclass or the subclass. So we kind of get inheritance for free. This is what it takes to implement a method. What would it take to call the method? This is the same client code that goes through and prints out just a grid of boxes for the spreadsheet cells. But instead of accessing the field directly, they'll call our fake method. They'll call getWidth, and they'll supply a pointer to the cell they want it to work on. And then whether that pointer is a pointer to the superclass or one of its subclasses, well, backing up a slide, this code we were just looking at will be able to get that width field and return it to the client code. So I guess a nice thing about this is after the client code made a spreadsheet that consists of different types of cells, this code doesn't have to worry about what kinds of cells they are. Each type of cell has a get, or getWidth works for either superclass or subclass. So this piece of client code doesn't have to have ifs that say, oh, if this is this kind of cell or this kind of cell. We've organized them so that this code works for either. So this is kind of like a way of doing encapsulation. We're giving client code a method that they can call rather than directly accessing the fields. In C, we can't really prevent them from directly accessing the fields. In Java, we can use access restrictions like private and public. And in C++, we have some of the same access restrictions that we'll see later. But in plain old C, especially if someone's willing to be sneaky, if they know a pointer to our object, we can't really keep them from looking at the memory inside that object. All right, so I claim we know how to make objects. We know how to simulate inheritance. We know how to simulate a constructor. We know how to simulate an instance method. Questions before we move on? I think the next thing I'd like to do is be able to override methods. And this is going to take some extra work. In Java, methods are easy to override. They're kind of the default. But you're about to see making a method so that it can be overridden is going to take a little bit of extra work. And even in Java, if you look at how it's implemented, methods that get overridden they do take more work. It's just they don't take any more code when you're writing in Java. But if you look at what's going on in the JVM, they are more complicated than methods that you don't have to override. Why do we want? I probably should have motivated this with what we want to do. I guess if we wanted cells to be able to print themselves out, the right thing to print depends on the kind of cell. Let's say for the superclass, we're just going to print an empty cell. We'll just print a bunch of spaces. But for the money subclass, let's have it print out a monetary amount. It'll print out dollars and cents for that. And then if we added other types of cells later, they might need their own print methods that did the right thing for that kind of cell. So we need a method, we need a function, kind of like, backing up a couple of slides, kind of like what we did with getWidth. But this getWidth does the same thing for any type of object. We need a method where the version of that method depends on the object. So if you call a print function for the superclass, it'll just print out spaces. If you call a print function for money, it'll print out a dollar and cent amount. And a way we could do this is with function pointers. How about instead of having the same method that works for every type of cell, we make cells so they carry around a pointer to a print method for that kind of cell. And that's what I'm showing here. How about if instead of just having a width, every cell knows how to print itself. And when I say it knows how to print itself, I mean it's got a pointer to a function you can use whenever you need to print that cell. This will be, since it's something every cell should have, well, just like the width field, the cell superclass will have it, and any subclasses will include that in their struct in exactly the same place. So we're going to go make the superclass a little trickier. It'll have a width, but it'll also have a pointer to a function for printing that cell. And every instance of cell will have a pointer to a function that just prints out a bunch of spaces. For the superclass, that seems like the right thing to do, just to print an empty cell. But for the subclass, since the money subclass has a dollar and cent amount, they'll still have a print function. It'll be a pointer to a function just like the superclass. It'll just point to a different function. we'll fill it in so that if you take the print pointer and you call the function it points to, well, for money, it'll call a function that prints out dollars and cents. For the superclass, it'll call a function that just prints out a bunch of spaces. So each subclass will fill in this pointer with a pointer to the right kind of print function. Since every cell carries around a pointer to its own print function, as long as you call that function via this pointer, you'll get the right version of this function. In C++, this would be called a virtual function. In Java, you would just say you're overriding this function. But here you can kind of see you have to plan for the ability to override a function. You have to have an object that's smart enough to know, oh, if you need to print me, here's the function you call. And then some other object, if you need to print me, here's the function you call. There were some chat comments. Any questions people want to ask? All right, so here's what we're going to do next. We're going to have to go back and extend our superclass. Now it's going to look like this. So this is the struct definition for cell. Still got a width field, but I snuck in an extra field before that, and it's what we were just talking about. It's the syntax is a little weird, but you'll recognize this as a pointer to a function. Print is a field, but its type is print is a pointer to a function that takes a pointer to a cell, so whatever cell you want to print, and returns nothing. I got a picture over here that it's just like the picture on the previous slide. So now every cell carries around its width field and a pointer to a function for printing that cell. Down here in the constructor, I have to fill in both of these fields. I'm going to initialize, so I'm alloc space for the new cell. I fill in its width field, same as before, but I fill in its print function with a pointer to the function I defined right here, a function for printing generic cells, for just printing a bunch of spaces. And that's what this does. Same syntax we saw before, this %s says print the string in a field width that's determined by one of the arguments. So here's how wide it needs to be. And for the string, I'm just printing empty string. I'm really using the padding. I'm using the field width to print all spaces. And then I don't really, once I've filled it with spaces, I don't really have anything else to print. So this is a sneaky way of just printing a given number of spaces. So cell objects have a pointer to, now they're made knowing that when you ask me to print myself, here's the function you need to call. They carry around a pointer to that function. Subclasses, so money objects, well, they start out looking just like a cell object, which means they have a width field and a print function, just like the previous one, but they add a monetary amount. Down here in the constructor, I make enough space for a money object, so enough space for all three of these fields. I fill in the same two I was filling in before, the width and the amount of money, but I also fill in my print function. But for these, I make them point to a different print function. So backing up, superclass, they're each made with a pointer to this function to print themselves. Subclass, they're each made with a pointer to this function to print themselves out as money. The print money function gets a pointer to a cell. That's the superclass. It had to be the superclass because we defined the print function back when we were defining the superclass. Cell doesn't know anything about all the different subclasses we might make for it. So this function expects a pointer to a cell. But since this function's only going to be called for money objects, if it gets called, we know that that's secretly a pointer to the subclass, to money. So we cast it. We take cell, we say, well, pretend that's really a pointer to money, and call it this. This is not a reserved word in C, so we can use it as a variable name. And here I'm using it as the obvious variable name. I'm using it to mean the same thing this means in Java. It's a pointer, it's a reference to the object in which you're currently running. So now I've got this as a pointer to a money object, and then I can look at its value field. And this is just printing it out as dollars and cents inside a particular width. So here's how to define methods. We've already overridden them, and we did it when we filled in this print field. I'll say it one more time. Whenever you make an instance of the superclass, you fill in its print field to a pointer to the right function to print instances of the superclass. Whenever you make an instance of the subclass, you fill in its print function with a pointer to the right function for that subclass. How do you use this? Well, here's client code that does more than just print out an empty grid of cells. Now I'm going to ask each cell to print itself using the method, using the trick we just talked about. So code is almost the same. I go through every element of my 2D array. I print out some vertical bars around the cells, but then when I get the cell at row I, column J, instead of calling a hard-coded function inside this cell, I'll go call whatever its print function points to. So C is a pointer to a cell. It's got a print field. So C arrow print gives me the value of its print field. That's a field in the struct, but it's a function pointer. So like any function pointer, if I take that function pointer and I put parentheses after it, it'll call the function it points to. So I call the print function on that cell. And if you back up, all of these print functions are expecting a pointer to the cell they're supposed to print. So I still have to pass that in. I know it's a little weird because C shows up twice in this expression. I'm using it once to pass it as a parameter to the function because the function's expecting it as a parameter. And I'm using it once just to look up the print function. If we were doing this in C++ or Java, just like calling any instance method, the compiler would do this part for me. I wouldn't have to explicitly pass in a pointer to the object I'm calling a function on. But here, since I'm doing it all myself, I have to pass in that parameter. Otherwise, print would be a void function and it wouldn't know what it's supposed to print. The nice thing about this code is this would work even with extensions. If we added new types of cells that weren't even around when we wrote this code, if they all had a print function and they all overrode it as necessary, we wouldn't have to change this code at all to get it to use new types of cells. Because we implemented a extensible way of doing function overriding. So that makes it easier to extend our program. We've got a couple more tricks that we need to do, but I see that we're out of time, so we might have to save those for next time. The main thing we have left to do is there are a couple of more tricks that our objects need to be able to do. And to motivate that, we're going to introduce the string. We're going to introduce a new subclass that instead of holding a fixed amount of, or a particular amount of money, can hold an arbitrary string. But we'll save that for next time. Thanks for your attention. I hope you did well on the exam. I'll hang around if people have questions. Good luck on Project 5, just one more after that. Have a good weekend.
Thank you. Have a good weekend.
Thank you.